All right. There's a lot of definitions here, but my claim is they're not as bad as it looks. I don't, it's easy for a math professor to say, right? But let's see what it looks like. So an average cost function, a lot of times, is a rational function or can be modeled by a rational function. So let's actually start talking about what is a rational function. So a rational function is a function that can be written as the ratio of two polynomials. So we've got a big mess going on here, but let's just focus on this part right now. The function is just one polynomial divided by another polynomial. That's all a rational function is. We talked about polynomials in 4.2. Well, if you divide them, that's a rational function. That's the only thing we're doing, dividing polynomials. And so what this messy thing on the right is, well, notice that this top thing, this is just a regular old polynomial. It's in like reverse order from what I usually write them as, but it doesn't really matter, right? So it's just polynomial with degree p. And on the bottom, there's a polynomial of degree q. They don't have to have the same degrees, these polynomials. They have a bunch of coefficients, a bunch of terms. These are their leading terms for each polynomial. Remember all these definitions from 4.2? All right, so this is what a polynomial kind of looks like. And so in example 2, here's another example of a rational function. It's a polynomial, in this case a line, divided by another polynomial, also a line in this case. So we're going to graph this, and we're going to start noticing some patterns about rational functions. 2x plus 4 over x minus 3. All right, so the first thing is we're going to need to zoom in. All right, and again, this looks just like our average cost function, right? To the right, this function gets really close to something. What do we think this function's getting really close to as we go really far to the right? Looks like it's kind of getting close to 2. I wonder where that 2 comes from. We'll talk about that in a future video. And then notice that as we go to the left, we're getting really close to infinity. And over here, we're going really close to negative infinity. What is our input getting close to? In our average cost function, as our input got close to 0, we were shooting off to infinity. But here, it's not 0 that our input's getting really close to, right? Oh. What's our input getting really close to when we're shooting off to infinity? Our input's getting really close to 3. So, oh gosh, the green screen is messing up my teeth. I'm going to have to go to the dentist. Anyway, so look at this function. And look at the fact that as we get really close to 3, the function's going bananas. What's the connection there? As a function goes to 3, as the input goes to 3, the input goes to 3, the output starts going bananas. Well, look what happens to this function. If our input is 3, if x is 3, what happens to our denominator? If x is 3, our denominator is 3 minus a 3. That's 0. Denominator of 0 is bad stuff in math, okay? So that's one of the things that we're going to talk about next. It's the concept of an asymptote. A vertical asymptote of a graph is a vertical line that the graph gets close to either positive infinity or negative infinity as those inputs approach that A. So let's just pause here and look. If I graph this, if I graph the line x equals 3, the line x equals 3 is a vertical line. And notice that as the inputs get close to this line, as the inputs get close to 3, the outputs are going up to positive infinity up here, or from the left, they're going down to negative infinity. This is a vertical asymptote. It's a line, a vertical line that the function gets really close to, shooting off to positive infinity or negative infinity. And then we have another definition for a horizontal asymptote. Well, that's going to be very similar. It's just going to be a horizontal line that the function gets really, really close to. So Looking at our graph, our horizontal asymptote, notice as we go really far to the right, the graph's approaching this purple line. The y value is approaching 2. As we go really far to the left, the y value is approaching 2 from below. So this is what's going to be a horizontal asymptote. Asymptotes are just lines that our function gets infinitely close to. All right, then. Example 3 says, what are the vertical and horizontal asymptotes from our last two examples? Well, we already answered this for example 2, right? For example 2, we just graphed them. Horizontal asymptote of y equals 2. Vertical asymptote of x equals 3. There they are. Again, the horizontal, we said was y equals 2. The vertical was x equals 3. What about example 1? Well, think about what asymptotes refer to. One asymptote is when things start going bananas, when that denominator is 0. Remember that when our input got close to 0, our average cost was going through the roof. That was our vertical asymptote, was when our input went to 0. So in example 1, I'm not going to box that. In example 1, right, our horizontal asymptote, let's skip that. Our vertical asymptote was when our input was 0. And remember, we weren't using x's and y's here. Where we're using quantity and average cost. So our vertical asymptote was when our input was 0. Our horizontal asymptote, remember what this graph looked like? It looked like this. So again, a lot of times we can draw asymptotes with like dotted or dashed lines. Then we had another horizontal asymptote that looked kind of like this. What was the average cost going towards? If we produced a ton of these items, eventually the average cost would approach 20. That's our equation. Average cost equaling 20. So again, we don't have y's and x's here. We have quantity and average cost. So this is what our equations look like. They're the same. These are exactly the same things, right? These two things. But our input is x in one, q in the other. And our output is y in one, average cost in the other. There we go. Let's get some practice with this. Find the vertical asymptotes of this rational function. Okay, so different kind of rational function here. We have a quadratic on top and a quadratic on the bottom. They're both polynomials. It's fine. What do you notice about the answers in relation to the equation of the function? I already got into that a little bit. But let's see what we can notice. So if we graph this, 5 plus 2x squared divided by 2 minus x squared. Whoa, this rational function looks pretty different, right? What's going on with this rational function? Well, now we have these pieces that we saw before. Now they're on the same side. We also have like this weird v piece or u piece in the middle. The rational functions can look a little different, but they have a lot of similarities. We'll be graphing more of these and we'll be seeing more of this. So let's start with the horizontal asymptote. I think that's a little easier to see here. Horizontal asymptote, as our input gets really big, what's happening to our output? Looks like our output's getting close to -2. And vice versa, right? As we go really far to the left, looks like our output's getting really close to -2. That's going to be our horizontal asymptote. The horizontal asymptote is something equals -2. Is it x equals -2 or y equals -2? It's y. Y equals -2. That's the equation of a horizontal line. And another way to think about it is we're looking at what are the y values getting close to. They're getting close to -2. All right. So, and if we graph that, y equals -2, hopefully, oh, look at that. So here it's getting close to it from the below. Here it looks a little weird because it actually gets above it, but it's still getting close to -2 from above. So it's okay if it crosses it. What matters is that it's getting really close to it afterwards. So even though it crosses it, it's not going to cross it again. Still getting really close to it. And again, usually these are graphed with like dashed lines like this for asymptotes. So what's our vertical asymptote? Well, it looks like we might have 2. Right? We're going off to -infinity. What's our input doing here? Looks like if our input's getting close to 1, maybe? What about here? If our input gets close to 1, we're going off to positive infinity here. So it looks like there's a vertical asymptote at x equals 1. See how that looks with our picture. There you go. Looks pretty good. That looks like a vertical asymptote. X equals 1. But in this case, there's more. Right? As we go this direction, let's zoom out so we can see this a little better. As our input's getting really close to, I don't know, maybe -2. As our input gets really close to, yeah, it looks like it's centered around -2. Looks like we have another vertical asymptote at x equals -2. And you can see it with this graph like so. So we have 2 vertical asymptotes here. And the question that it is also asking is, what do you notice about the answers in relation to the equation of the function? Let's rewrite k of x real quick. What happens if we factor the denominator? You could do some factoring steps, but what you're going to get is 2 minus x, and then 1 plus x, I believe. Let me just double check in my head. If we multiply that out, we get a 2, we get a -x squared, minus x plus 2x. Oh wait, I think I have my directions flipped. All right, still have the 2, still have the -x squared. And the cross terms are minus 2x plus an x, so that should be minus x. Okay, this is what we got. So what do you know about the connection between our vertical asymptotes and our denominator? It's just like before, right? If x is positive 1, our denominator is 0. Big problem. That's why there's an asymptote here. We'll talk about that in the next video. Similarly, when x is -2. Horizontal asymptote, it's not really obvious where that y equals -2 is coming from. If you see it, that's great. Otherwise, we'll cover it in a future video. Let's end this with just a little practice, very similar to what we had before. Pause the video, try to graph this on Desmos, and see if you can find the equations of all the asymptotes. All right. It just says vertical asymptotes, but good practice if you can get horizontal asymptotes too, if there are any. All right, x minus 2 over x squared minus 4. All right, then what we got here, okay, looks like we got horizontal asymptotes and vertical asymptotes. Like our horizontal asymptote, this function's getting really close to 0 on either side. Yeah, it looks like we got a horizontal at y equals 0. That looks right. Again, it didn't ask for horizontal, but it's good practice. What about vertical? Well, as our input, maybe zoom out, as our input's getting maybe close to -2. Yeah, as our input gets close to -2, the function shoots off to positive infinity or negative infinity. Great, there we go, that's the answer. Now, that's pretty much the end of the video. But you might be wondering, anybody who's like really, really on top of things might say, Jason, this denominator factors to x minus 2 and x plus 2. Over here, we had 2 asymptotes when the bottom was 0. So how come over here, we only have 1 asymptote? How come only this guy on the right makes an asymptote and this guy on the left doesn't? Why do you think? How does this function look a little different? What's unique about the guy on the left that's not giving us an asymptote? Cliffhanger. We'll answer that in the next video, okay? So work on these ones, vertical asymptotes. We'll talk about what that left situation is in the next one. Enjoy. Bye-bye.